Welcome back to Mechanical Engineering Made Simple. Show your support with a like, a follow, or a comment. Let's keep leveling up together. All right, today we are digging into the real mechanics of designing rotating shafts that actually last. We're tackling those core engineering questions every designer faces. You know, the ones that separate what kind of works from what runs forever. Okay, let's dive into this.
So here's what we're going to walk through in this explainer. We'll start with the biggest question of all, sizing. Then we'll get into the nitty-gritty of precision with tolerances and bearing fits. After that, we'll see why tiny little details in geometry can create huge stress points. And we'll challenge the idea of focusing only on stress instead of deflection. And finally, we'll bring it all into the real world with fatigue, installation, and balancing.
All right, let's kick things off with the first, and honestly, the most common question every single designer bumps into: sizing. It sounds simple, but it is the foundation for the entire design.
So how do you pick the right shaft diameter? This really is the million-dollar engineering question, isn't it? It seems so straightforward, but getting it wrong can be an incredibly costly mistake.
You know, the answer isn't some nice, clean formula you can just plug into a calculator. It's not just about handling the torque. The right diameter is the one that manages a whole system of competing needs. All the forces, the fits, and its fatigue life.
So here's the crucial point. Torque gives you a baseline. It's your starting point. But that's all it is, a start. From there, you absolutely have to account for bending forces, from the weight of all the components, and any other process loads pushing and pulling on that shaft.
And it doesn't stop there, not even close. You've got to factor in dynamic loads that are changing all the time during operation, plus any tension from things like belts or chains. All of this stuff contributes to the shaft's tendency to deflect or bend, and that deflection is very often the real thing that limits your design.
Okay, so once you have a ballpark size, you have to start thinking about how other parts are going to fit onto it. This is where we get into the language of precision. We're talking tolerances and fits, and it becomes absolutely critical, especially for bearings.
For bearings, we almost always use what's called an interference fit. So what's that? It just means the shaft is made intentionally just a tiny bit larger than the hole in the bearing. This controlled tightness is what keeps the bearing from slipping or creeping on the shaft, which would generate a ton of heat, cause wear, and lead to a very fast failure.
Now, this is the practical truth right here. The golden rule you got to remember is +0, negative only. You never, ever want the shaft to be oversized because it'll just destroy the bearing. These numbers you see here are typical commercial tolerances that give you a good, solid fit without forcing you to specify some crazy expensive custom dimensions. But get this, a shaft's strength isn't just about its raw diameter. The actual geometry, especially those spots where the diameter changes, is often the most critical factor in whether it's going to last or not.
And this is one of the most vital lessons in all of machine design. Sharp internal corners are killers. They basically act as stress concentrators, or to put it more bluntly, they're crack starters. This is where failures begin.
This chart shows the danger perfectly. See, stress isn't uniform. The moment you have a sharp corner where the diameter changes, stress just gets piled up and multiplied right there. A nice gentle transition lets the stress flow smoothly, but a sharp corner can easily double or even triple the local stress, creating a weak point where a fatigue crack is just waiting to start.
So we've talked a lot about stress, but that leads to a really counterintuitive idea that completely changes how a lot of shafts get designed. In many, many cases, stress is not what you should be worried about most.
And in so many practical applications, the answer is a resounding yes. It's a fundamental shift in thinking for a lot of designers, but it's a crucial one.
Think about a number like 30 thousandths of an inch. It sounds like absolutely nothing, right? I mean, it's impossibly small. But in the world of rotating equipment, that is a huge amount of movement. And here's why. If your shaft deflects more than that tiny amount at a mechanical seal, that seal will fail, period. If it deflects too much at a bearing, the bearing gets misaligned and wears out way too fast. So even if the stress in the shaft is totally safe, excessive deflection makes the entire design fail. That's why deflection is so often the true governing constraint.
Now, let's talk about a force that you can't even see, but that is working on a shaft over its entire life: fatigue. It truly is the silent killer of rotating components.
This quote just nails it, doesn't it? Every single rotation puts the shaft through a cycle of bending and twisting.
Over millions and millions of cycles, these small stresses can cause microscopic cracks to grow and grow until it leads to a sudden failure at a load that's way below the material's static strength limit.
So, to combat this, engineers design with fatigue safety factors. As you can see, these are pretty standard minimums. We'll design the drive end to be at least 1.5 times stronger than needed for the fatigue load, and the stub end even stronger. It's all about providing a buffer against that relentless, cumulative damage from all those cycles.
You can have the most perfect design on your computer screen, but if it's not handled correctly out in the real world, it's all for nothing. So let's look at the crucial final steps: installation and balancing.
A perfect shaft can be completely ruined by a bad installation. These are the silent killers out in the field. Pressing bearings on crooked, which creates a wobble, using dirty surfaces that prevent things from seating right, or tightening locking collars in the wrong order. Any of these little mistakes introduces unintended loads that will absolutely kill your bearings and your shaft.
And finally, let's bust a common myth. A lot of people think balancing is only for high-speed equipment. That is just wrong. Even at 100 or 200 RPM, an unbalanced shaft assembly creates a centrifugal force that just hammers the bearings with every single rotation. This vibration accelerates wear, it causes deflection, and it leads to premature failure. Balancing is not optional, it's a requirement.
So, to wrap this all up, I want you to think of your shaft not as just a simple component, but as the heart of a complex system. The real question is, have you truly considered every single interacting element, from all the bending forces and stress risers in the design phase, all the way to the tolerances and installation practices on the factory floor? Because that holistic view, that's what separates a shaft that works from a shaft that lasts.